Hello everybody, my name is Nadim Amari, thank you for the introduction. So just a little bit glance, we are similar to the Austrian Institute of Technology, but we are the Swiss Institute of Technology. We are located at different locations across Switzerland. Our objective is to exactly what you do at AIT, is to transfer technology from academia onto the industry. We mainly focus on two pillars. One is applied research, and the second topic is about tech transfer. We have lots of, coming from the Swiss industry, we are working a lot with the watch industry. We have expertise in ultra low power operating system, photovoltaic cells. We have embedded AI in multiple applications. We are known for miniaturized atomic clocks and also for automated machines for personalized skin re-engineering. Our main focus at CSM are threefolds. One is digital technology, precision manufacturing, and sustainable technology. I am mainly focused on the upper corner of the digital technology, where we are working on ASIC for the edge, data and AI, and vision and IoT. My talk today is all about metrology through imaging. Today, we know on the state of the art, we have three scenarios in which we are doing metrology on a machine. The first one is either through optical encoder. We have big names like Heidenhain. We also have interferometry, which is quite used also in metrology solution. And the last, let's say, state-of-the-art and most relevant topics is capacitive or inductive sensing. And these are really dedicated for proximity short stroke actuators. The main dilemma about these types of technologies is twofold. One, it's a type of point measurement, so you don't have an image which is being formed. And the second aspect, it is a single degrees of freedom measurement that is being done. We are not able today, with any of these technology, measure multiple degrees of freedom at the same time, okay? So this is where we come in with a novel type of technology which is based on shadow imaging. The principle is quite simple. I need the laser pointer for a second. Okay, so we have three components. The first component is LED source, any type of illumination which is taking place. The second component is a mask, which is being done by simple lithography or any type of grating mask that is possible. And the third aspect is an imager. Okay, and here the main point is that we are constructing the full image, the full shadow image. On the left is a simplified representation, okay, and on the right is a typical implementation where we have an imager, a pattern grating, and on that pattern grating we have fiducials to ensure the repeated phases are in line, and the third aspect is a light source. Okay, to give you the idea of how the added value of this type of metrology system, if you compare it to a standard approach where you have a single LED, an optics, and a sensor, the spot size that you end up on the detector is a few pixel size width. Okay, and the resolution that you end up with is the order of magnitude of the pixel pitch that you have. We could interpolate, but we end up with something in the range. On the typical imager, I have a pixel pitch of 5 microns. We end up with a precision limitation of 5 microns. Now, in contrast, if we looked at the space coder approach, which is based on shadow imaging, here we are using the full detector for our system, and we have the full projection of the shadow mask on the sensor. And this allows us, one, to be able to average all the errors that we have on that system, and we are able to reach sub-pixel resolution up to 10 nanometer. The 10 nanometer here is actually the intrinsic limitation of any type of detector, any type of commercially or industrial detector. Based on the electronic shot noise that we end up with, we are not able to go beyond 10 nanometer. When we talk about the imaging, the processing pipeline, it is quite simple. We have the light incident on an encoder disk or a diffraction grating. Okay, we capture the intensity of the pixel, then we sum along the rows and we sum along the columns. Once we have that, we convolve it into a sine, cosine, and based on the angles between that we are able to get, we are able to get the phase measurement of the shadow image that we are getting, and getting the position of the LED source relative to the detector itself. In terms of stability for the system, we measured along different type of stability solution, and we have recorded measurement of 48 hours, which is approximately 3 million measurements. Okay, we had in a fixed environment, dark condition on the stable condition, and we are able to get a standard deviation of 10 nanometer and a peak-to-peak variation of 80 nanometer. This is along all degrees of freedom, so X, Y, Z, and also along the posture. Okay, we are able to decrease it a bit more by removing the long-term repeatability due to the thermal drift by going something in the range of 15 nanometers when we consider two measurements which are 2 hours apart. So here the main point that I'm explaining, that the simplicity of an LED, a shadow mask, and an imager is able to get nanometer level precision. Based on that, we did multiple technology transfer. One is used in the hexagon touch probe, in which the full system by itself is able to reach something in the range of 300 nanometer. But the most interesting part is the triggering, which is limited to 5 microseconds. So we have 5 microseconds in which we are doing the exposure, we are doing the processing, and we are sending the information of the relative position of the touch probe during operation. This is very important, specifically when we are touching a contact surface, and we want to be sure that the contact point is accurately sampled. Okay, all in all, the full system is, including the mechanical assembly, we are at 300 nanometer. And for that system to be able to reach the 5 microsecond cycle time, we had to develop a dedicated ASIC. The dedicated ASIC for it, which is embedding both the imager and the processing required for it. Another application showing a different axis of the technology is used in the medical for knee replacement, and this is showing the dexterity of the technology that we are offering. So here we are by no means in the range of a nanometer, we are in the hundreds of microns, but mainly because we have a field of view of approximately 90 degrees and a temperature range from 10 to 30 degrees. The layout is still the same. We still always have an LED sensor, okay? And on top we have a mask, a lithography mask, and an imager. This is already transferred to one company, Medivation, which they are already implementing in lots of applications. Now, having said all of that, everything is nice and clear, but we have an intrinsic limitation inside the space coder technology inside of shadow imaging. So if I take the intrinsic limitation of a sensor, which is approximately 10 nanometer, considering shot noise, electronic noise, and so forth, okay? And my shadow mask is located at a distance d1 from my sensor. I cannot be completely, I cannot glue my shadow mask directly on the sensor because I don't have any shadow anymore, so I need a certain distance. And the object which I am trying to measure is, for example, at 1 meter away. Okay? The main problem is that I have an amplification of my sensor noise from the sensor plane onto the object plane, meaning that if I have 10 nanometer at my sensor level, I'm going to end up with 10 micron error I'm getting at 1 meter away. Okay? The main point, the main approach in which we are able to overcome this limitation is by increasing the distance d1 between the shadow mask and the sensor. The problem with that is that we end up with diffraction and we lose on the resolution, because now the grating that we are getting on the sensor are no longer consistent with the shadow mask. Okay? So we have these two limitations that we are not able to overcome. And this is what the novelty of our technology is, the possibility that we leverage the talbot effect. So the talbot effect is quite simple, in which if you have a plane which is a plane wave incident on a repeated pattern, the diffraction will be periodic, okay, until we reach the point of the sensor. And for that, this allows me to increase my distance to the shadow mask, increase the distance between my sensor and my shadow mask. Meaning now the error that I'm getting on my sensor, which is stuck at 10 nanometer, I'm able to decrease it onto the object plane. Okay? And here on the left is the diffraction pattern for the talbot effect. To better visualize it, I did a small animation. I try to see if it works. Yeah. On the bottom you see the actual images that we are getting on the imager, and on the right is an animation in which we are seeing how the mask is moving. Let me repeat it one more time so you can see it a bit better. Okay, so we see that somewhere along the line we are losing focus, then we are capturing focus. So we could be multiple talbot distances, put the multiple talbot distances between the mask and the image. This is what we refer to as the talbot carpet. And with this type of system, I'm able to reduce the projected error from the sensor, which is order of magnitude of 10 nanometer for a 5 micron pixel, to something which is sub-nanometer, as you're going to see in the next slide. This is the experimental layout that we put in our lab, and here I have with me, if I'm able to find, yeah, thank you. No, I just need this one. Yeah, and I have with me the same experimental setup that we built for a demonstrator, which at the end I'm willing to show it to you guys. Okay, and here what we are doing, this is the this is the laser. This is the mask, which is extremely close to the laser, and the imager is several talbot away from the imager itself. Okay, and we are measuring. We're doing a step for the imager of approximately 10 micron, and we are capturing this with 650 increments. So meaning phasing, we are getting 650 increment, and this leads us to a resolution of approximately 0.5 nanometer 1 sigma. Okay, and here we are measuring in 2 degrees of freedom. I'm measuring, sorry, in 3 degrees of freedom. I'm measuring the XY plane, so everything which is perpendicular to the scanning, to the optical axis, and also the Z axis, I'm also measuring it. So in summary, we developed a metrology system which is based on shadow imaging that leads to a 10 nanometer resolution on the sensor plane. The fact that the simplicity of the processing pipeline that we have, we are able to push with a dedicated ASIC something between the 40 to 60 kilohertz in terms of processing time, and we are able, because it's an image-based system, we are able to get 6 degrees of freedom from a single point. Okay, of course it's a lensless solution, so we cannot refocus any of the optical rays. So we have the issue of the diffraction, which is due to the distance between the mask and the imager, and this is where we introduce the talbot-induced diffraction. So this is for once physics working on our side, and in which we are able to increase the distance between the mask and the imager, and decrease the resolution that we are able to get on the object level to something of the order of 0.5 nanometer. Okay, this is it from my side. I'll take the opportunity to say that CSM is now having the 40th anniversary by the end of the year. Thank you very much.
Thank you very much.